let us now take a look at how you write an electronic configuration for an atom. All right. Okay. For example, carbon. Okay. If you take a look at the carbon, you realize that carbon has a total of 6 electrons. So using this staircase, which you need to make sure you memorize and be able to utilize it in the exam, we call it a staircase. Maybe I introduce that first, because in the first electron shell, there's only one subshell, 1s. In the electron shell number 2, you have 2 subshell, 2s, 2p. Third electron shell will have 3s, 3p, and 3d. And the fourth electron shell will have 4s, 4p, 4d, and 4f. 4f, by the way, will have 7 orbitals. All right. The shapes are not in the syllabus, so we're not going to cover them. But you need to know that the 4s subshell can at most carry a maximum of 14 electrons, since it has 7 orbitals. All right. Finally, when you hit the 5th electron shell, you start to realize that the subshell remains the same. And then obviously, when it goes to the 6th electron shell, it starts to decrease actually in terms of the number of subshells. And it makes sense because as the electron shells get further away from the nucleus, obviously the electrostatic force of attractions on them will be weaker. And so there are less electrons they can actually hold together. And last but not least, when you hit on the 7th electron shell, there'll be a 7s and then a 7p. Okay, so that's how we interpret and remember the staircase, which we call it. And heading back to the example on carbon, and carbon has 6 electrons, we will have to fill if we have 6 electrons, we have to fill in the order that the arrow is indicating, which means we have to fill up your 1s first. And 1s as a whole could only hold up a maximum of 2 electrons. So that's how your 1s2 come about. Then we'll then fill up the next subshell, which will be your 2s. Again, your 2s can hold 2 electrons. That will be 2s2. And finally, the final 2 electrons will then go to 2p. All right. So in terms of the electronic configuration that we're writing, will be called 2s2, 1s2, 2s2, and 2p2. Obviously, 2p can hold a maximum of up to only 6. If you want to build it down, break it down into orbital level, we could write it as 2px1, 2py1, and 2pz0. Also bear in mind that electrons, as far as possible, want to be singly occupied. In terms of when they get into the orbital, they prefer to be singly occupied. Only when all the orbitals of the same subshell has been filled, then they will be they will then go into a situation whereby you'll be doubly occupied. Okay. Also bear in mind that certain atoms, when they are heated, they could undergo excitation, and some of the electrons could actually hop. All right. So like in the case of carbon, if it's excited, one of the electrons from the 2s subshell will migrate to the 2p, and therefore in this case you end up with 2s1, 2p3 actually. All right. And in terms of breakdown, will be 2px1, 2py1, and 2pz1. All right. Okay. Other ways of representation of electronic configuration will be via boxes like this. So let me run through the example on scandium. Okay. So let's take a look at scandium. So scandium in the periodic table is here. So total you have 21 electrons. So if it has 21 electrons, there'll be a bit of math that we need to do. So you can see that 2 electrons will go in here, another 2 will go in here, another 6 will go in here. So total, you would have actually deployed 10 electrons. 2 more go into the 3p, and then the 3s and 3p, which will be total of 8. And then bear in mind, it's not going to fill up the 3d first, because based on the staircase, the arrow that is indicated, you have to fill the 4s. So therefore, in this case, at this stage, you would have filled 8 in 3p and 3s and 3p, I'm sorry, and you would have filled 2 in 4s. So at this stage itself, you totally deployed a total of 20 electrons. So the final electron will have to go to your 3d. So in terms of electronic configuration, the way that you write it, it will have to be 1s2, 2s2, okay, 2p6 that we mentioned, 3s2, and 3p6. Although we fill up the 4s2 first, but in terms of writing of electronic configuration, you ought to be saying 3d1, then followed by 4s2. Okay? As you probably would have been able to see, that another way to represent them is to actually draw them in boxes. Every box represents an orbital. So in the case of all the 1s, 2s, and the 3s subshell or 4s, they are represented by only a single box because every of these s subshell only has one orbital. In the case of p orbitals, it will be represented by 3 consecutive boxes joined together, as indicated down here. Okay, so this will be the 2p, and this will be the 3p. And obviously, you will be able to see by now that the electrons are represented by a set of half arrows, one pointing up and pointing down, representing that they have different spin. All right. And so finally, what is interesting is that 3D subshell will be represented by 5 consecutive boxes because it has 5 orbitals. And in the case of scandium, it only has 1 electron, and therefore you represent with a half arrow, all right, to represents the single electron. And obviously, this final part is actually your 4s subshell. Okay, so this is the way that we uses the staircases to deploy or to determine the electronic configuration. So we have more examples that you can look through, all right? So divided into this. But what I'd like to do in the final part is to show you the shortcut as to how we could very quickly come up with electronic configuration of certain elements, all right? So practically, we categorize the periodic table into 3 blocks. We call the S block, the P block, and the D block. Let me run through the S block first. This is the S block, okay? This is the P block. Why do we call them as such? And how is it related to the S and P subshell? You will find that in the case of S block, all the elements in group 1 will end their electronic con with S1, while in group 2 will end with S2. In the P block, the group, okay, if I can shift it up, the group 13, all right, will all end with P1, and the group 14 with P2, P3, 4, 5, and 6, all right? So let me give quick examples. So if you now were to say that I want to find out the electronic configuration, say for potassium, all right? So what I need to do is just to count the period number. So I count the period number for potassium will be 1, 2, 3, 4. Because it resides in group 1, it will end with 4s1. So how I do it is that we can then pull it back to look at the staircase, all right? So if you now look at the staircase, understanding that potassium electronic con ends with 4s1, or circle the 4s1 here, and straight away I can say the electronic con for potassium is 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. Okay, let me give you another example. So let's take a look at selenium. So selenium is period 1, 2, 3, 4. Because it resides in P block, and as we said, it's P1, P2, 3, and 4. So therefore, its electronic con will end with 4p4. So let us see how that helps us by now deploying the staircase. If we know it's 4p4, I'll circle that. So the electronic con of selenium would actually be 1s2, 2s2, 2p6, 3s2, 3p6. And because the 3d will be occupied as well, so it's 3d10, 4s2, 4p4. That's how you determine it. Finally, let's take a look at the D block, or the transition metals. So as I earlier mentioned, you have the S here, you have the P here, which we explained. So let me now focus on the D block. This is the D block. The D block has 10 columns, respectively from D1, D2, so on and so forth, until D10. Okay, and also remember one key thing is that the first row that you see down here, which resides in period 4, 1, 2, 3, 4, actually this is called the 3D block. The next block that you have is your 4D, okay? Then your 5D is here. And obviously those wondering where the F block is, this is the F block. Okay? So for us, let's focus on the D block. So a quick examples on this will be we look at vanadium. So vanadium is a 3 inside the 3D block, and because it is D1, D2, D3, we will say straight away its electronic configuration ends with 3D3. Okay, so let us move to the D block. So for the case of 3D3, I will circle this as 3D3. So I'll say it's 1s2, 2s2, 2p6, 3s2, 3p6. Although it's 3D3, but I need to remember it's 3D3, and I have to say it's 4s2. So that's the electronic configuration for actually your vanadium. Okay. Remember that there's actually 2 anomalies in the D block. So one of the first anomaly is actually the chromium. As far as chromium is concerned, you'll find that a lot of them, well, a lot of us who tends to deploying the shortcut method will arrive at the conclusion it's supposed to be 3D4 4s2. Let's take a look at the periodic table. All right. If you look at it, this is chromium. So it's D1, D2, D3, and D4. So actually, we ought to think it's 3D4 4s2. Actually, it's not. It is 3D5 4s1. Why? The reason is because that by putting 2 electrons in the 4s, they are actually repulsion. And when you arrange the 3D, when these subshells, 3D subshells has 4 electrons, the energy gap between 3D and 4s becomes smaller. So it is now viable for electron from 4s, which is lower, to jump over to the 3D. So in summary, you need to see that you have your 4s here, which is both occupied, and you have your 3D here with the 5 boxes, and as explained, they are only singly occupied. Okay, so one of the electron could actually hop over. So end up, the correct electronic configuration will end up as 3D5 4s1, which is more stable because by doing so, every orbital will only has 1 electron. Okay, the other anomaly is actually your copper. Copper in the periodic table, if you look at it, should be 3D9. So if you count that, it's 1, 2, 3, 4, 5, 6, 7, 8, 9. So it ought to be 3D9 4s2. In this case, it's not. The reason is that once the 3D subshell holds 9 electrons, the energy level of the 3D will now be lower than that of the 4s because electrostatically it is attracted by the protons or the nucleus. So once it's lower, the ideal will be to occupy subshell with lower energy level first. So therefore, because of that, electrons in 3D will be fully occupied. So it becomes 3D10, and the remaining electron will then go to the 4s subshell. With that, we completed electronic configuration.